I'm excited to tell you today about some ongoing early stage work with Carlos Bonet and Jay Sethuraman, both of whom are at Columbia. The type of setting that we're going to be talking about are what I call selection problems. So selection problems are settings where an organization has a set of applicants. And in the context that we're going to consider, we're going to assume that there's some sort of default ranking of these applicants, but that this default ranking doesn't capture everything you might care about or want when making decisions about who to select. Right? So there are going to be some additional considerations, which that's sort of the affirmative action in the title of the talk. So affirmative action can mean many things, but in this context, I really just mean other considerations you want to incorporate that are not captured by your default ranking of applicants. And so there's many, many examples with these features. So for example, many schools might want to favor students from the neighborhood or low-income students, but maybe only for a fraction of the spots in that school. In the United States, we have a diversity visa lottery that has upper quotas on the number of people who can be from any one country or any one region that are selected. In India, there's a very ingrained form of affirmative action trying to help disadvantaged castes and women, people with disabilities. Chile actually had a really interesting experience recently where they were trying to rewrite their constitution. And so they elected a set of representatives to be involved in that rewrite. And they did this by vote, but they also said we're going to put some constraints on the final body that's involved in this. So it has to be half women, have to be a certain number of people from indigenous tribes, and so on. So these types of policies come up all the time. And today, I'm going to give a talk in sort of two parts. So the first part is going to be talking about affordable housing allocation in New York City. And this is an application that I've thought about and written papers on in the past. And the second part is going to be the theory that we came up with, not totally inspired by this, but inspired by this and many other settings. And so this will be the work with Jay and Carlos. And so we've got sort of theory and practice, and I debated, should I really just focus on one of these because then I can go in more depth, but I decided in the end to go for it. So we're going to have a little bit of an ambitious talk trying to fit in both of these topics. But hopefully this means that for those of you who are more interested in sort of practical applied things, you'll enjoy the first part of the talk. And I just think this stuff on affordable housing is very cool. So I wanted to fit it in. So let me tell you a little bit about affordable housing lotteries in New York. So in New York, developers get tax breaks if they offer a certain number of units in their apartment at affordable rates, as determined by the city. And so anyone who wants to qualify for these tax breaks has to list them on the city's website. So here's what a listing might look like. You go to housingconnect.com and you can see all of these different buildings. And then there's some application window. And after that window closes, the city takes all of the people who applied and places them in a random order. And then gives that list to the developers and says, okay, here's your list of applicants. Here's the lottery order in which they were placed. Now start at the top and start sort of screening and placing these applicants. So you might think, for example, here's a building, One East Harlem Residences. You can see it has 268 apartments available. And you might think, okay, great. So assuming everyone's eligible, the top 268 people in the lottery are going to get a spot in this building. As it turns out, it's actually much more complicated than that. So first of all, there's different layouts, right? So you have a studio unit, a 1 bedrooms, 2 bedrooms, 3 bedrooms. And so, for example, if you're a household with 4 people in it, you're not eligible to be placed in the studio or 1 bedroom apartments. You have to receive a 2 or 3 bedroom apartment. The second component of eligibility is your income. And actually different units are targeted towards different incomes. So these ones shown here are all targeted towards people making 40% of the area median income. That's what AMI stands for. But in the same building, you also have essentially identical apartments that are targeted towards people making higher incomes, up to 165% of median income. And so your eligibility is really unit by unit, and it depends on both your household size and your income. And if that weren't enough, we actually, not only do we have that set of policies, in addition, the city has what they call preferences, which says across the building, we want a certain percentage of the apartments to go to people with disabilities, to go to community board residents, so people who already live in the neighborhood, to go to city employees. 5% of units usually go to city employees. So it ends up being quite a tangled web of sort of requirements that developers are forced to navigate. And actually, this community preference policy is very interesting. So as I said, it gives 50% of the units in each building to people who already live in the neighborhood. So here's a drawing of the different community boards, community districts in New York. But it turns out there's been a lawsuit over this policy that's currently ongoing. And I don't have time, unfortunately, in this talk to go into the details of that lawsuit. But I did create several video blogs on my website. And so I encourage you to go check those out, because I think it's really interesting to sort of see what types of legal arguments are being presented. Both sides hired PhDs to do analysis. I would say both sides hired analysts didn't do a very good job, as far as I can tell, of actually analyzing that question. So it's an area where I think people like us could maybe help shed some light on important societal questions. But for this talk, all I really want to talk about is to say, okay, so we've got all of these complicated policies. These are what I would call affirmative action in some sense, in that we care about the number of people of households of different sizes. We care about how many people from very low income families versus high income families are being assigned. And then we also have these lottery numbers, and we want to incorporate those in some way to try to make it fair. And so if I were a developer handed all of these policies, I would say, well, what the heck should I do? How do I actually proceed to screen people? And so here's the process that developers have been told to use, which is, okay, first you're given the lottery numbers and the kind of ordered list of applicants. Then you start looking for people that satisfy the sort of minimums that the city has imposed. So you look for people who have disabilities, and you keep placing them until you've filled 7% of your units. And then you go back and you look for people who are from the community, and you start back at the top of the list, and anyone you haven't placed so far that it's from the community, you try to place them. Then once you've done that, you go back and you look for city employees for the 5% of units that are supposed to go to that group. And then finally, you go back to the top one more time and kind of consider anyone else until you've filled up all of the units. Any questions about this policy?
I have a question. So what about applicants that meet multiple criteria? Do they get a special treatment?
Great question. So that is not going to affect your placement on the list. I'm not going to sort of elevate you because you satisfy multiple criteria, but I will count you towards both quotas. So for example, if I place someone with disability preference and they also happen to be from the community, then that's one fewer apartment that needs to go to someone from the community in the next phase.
Got it. Thank you.
Yeah, so this is the algorithm they're using. I think it seems like a reasonable way to try to satisfy all of these constraints. The question is, what are the consequences of using it? And it's really, I would say, not clear how one would analyze this. What I'm going to try to explain to you in the next few minutes is my belief, which is that actually this policy is going to have the following consequence. Among the units that are set aside for low-income applicants, those are mostly going to go to people from the community. Whereas among the middle-income units, those targeted towards people making 130% or 160% of median income, those are mostly going to go to people from outside of the community where the building was built. And so sort of this is not an intended or stated policy goal. It's more just a consequence of using this algorithm. And the key kind of facts that drive this finding are, one, competition is highest for low-income units. So basically, there aren't that many people at 165% of median income who are looking at these affordable units relative to the supply of those units. And then second of all, people are applying from all over the city. So yes, there are a decent number of people who apply from the community district, but because there are 59 community districts, most applicants to a given building don't benefit from community preference. So because all of those policies are a little bit too complicated to think about, let's just use a simple example here. I'm going to assume that we only have one type of unit, so call it a 2-bedroom apartment. And we have two non-overlapping income ranges, so low income and middle income applicants. And I'm going to ignore the disability and municipal employee preferences and just focus on community preference. And finally, I'm going to assume that all applicants are eligible. In practice, you sort of verify eligibility online as you screen each applicant. But let's just, for now, assume that all applicants are eligible. Okay, so suppose we have a building that received 1,000 applications. 20% of these applicants are from the community district, but the other 80% are from outside. And 90% of the applicants are in the low income category. So that's going to be much more competitive. And so here's our 1,000 applicants kind of spread across 4 cells, indicating whether they're low and middle income and whether they're from the community or not. And now we have 100 units, 100 apartments to assign them to. And we say half of them should go to low income people, half of them to middle income people. We've fixed that for whatever reason. And in addition, we want at least half of these apartments to go to people who already live in the community. So that's going to be an example. Now, the question is, what happens when we apply the previous algorithm to this example? And first, we could actually do it and say, what would happen if we didn't have the community preference policy, right? So if we just got rid of this green constraint, and we just had 50 middle income and 50 low income, what would happen? Well, this is what would happen, right? We'd end up filling each of those units. And most of the units in both categories would be filled with people who are from outside the community, because most of the applicants are from outside of the community. So what happens when we add the community preference policy in? I claim we're going to get a distribution that looks something like this. And what I want to highlight is that you would expect, adding community preference increases the number of people from the community, that's the left column, who get allocated. But what's interesting is here, it really increases that number for low income applicants, but in this example has no effect for middle income applicants. And the question is, why do I claim this is happening? Well, in essence, the point is that the city is not saying 50% of the low-income units should go to community residents, and 50% of the middle-income units should go to community residents. It's just saying 50% overall. And so when you start by trying to fill seats with people from the community, you are mostly going to accept low-income applicants, just because most applicants are low-income. And so sort of the low-income applicants claim all the community spots. Or I should say, community members claim all the low-income spots is maybe a better way to put it. So let's actually kind of walk through that. So our first pass in this algorithm is to take the top 50 people who are from the community. And so we do that. And once we do that, we've satisfied the community preference policy. And at this point, we've taken 50 people, we've filled our community preference quota, 90% of those people are going to be low income, just because 90% of our applicants are low income. And so that's where we get these two numbers. Now we go back at the top of the list and we try to accept other people who we can. Very quickly, we're going to run out of low income units because those have already mostly been filled. And so now the remaining people that we take have to be eligible for the middle income units. And we actually get pretty far down our list, and this is kind of the final distribution that we get. And so I think this is kind of surprising that you only get 5 low-income people not from the community district. In particular, you might have person number 6 on the list, right? They were told they're applying for a building with 100 units. They got the 6th best lottery number of everyone. And you're telling them, sorry, we didn't have space for you. And they might ask you, well, why not? Like, why? This seems like I got a great lottery number, I should be housed. And you would say, well, you were skipped over in the first pass because you weren't from the community, and you were skipped over in the second pass because we ran out of low-income units. And they would say, well, but wait a minute, you accepted a low-income person from the community who's ranked way below me in the lottery order, and you didn't even need to do that. Because if you look, actually, one thing to notice is we actually ended up taking 55 members from the community. So we sort of overfilled the community quota when applying this algorithm. Now, I don't necessarily know that this is a bad thing. What I do think is that this is not recognized, right? So I read like 140 pages of analysis of what's going on, and no one sort of made this point in a clear way. And so I think it's an unintended consequence of the particular algorithm they're using, because we could be choosing, for example, a different distribution that satisfies the same constraints. Right? So even maintaining all of the rules about low income, middle income units, et cetera, we could just be choosing different applicants to satisfy that. And so this is kind of, I guess this is what I wanted to say about New York housing specifically. So this would be a good time for any questions about the housing application before I sort of zoom out to selection problems more generally. Okay, so and if you have other questions, feel free to just jump in. You don't need to wait for me to sort of pause and invite. But so what do I take away from this? What I take away from this is that we have a complicated set of policies whose consequences are difficult to analyze and understand. And it's sort of not obvious if you make some change to the algorithm, how that's going to affect the final set of people that you select. But it really matters, these changes to the algorithm. And these types of findings have come up over and over again in different applications, right? So there are papers pointing out that in Boston, they made a change designed to help people from the neighborhood get spots in schools, but it actually didn't really do that. In India, there are cases where actually you could be hurt from by declaring that you are of a minority group that's supposed to be benefited from the policy, but actually the way the processing algorithm worked, it might actually harm you to declare that. And then this is an example where I would say it did have the effect of increasing the number of community residents that were selected, but it also had this unintended side effect, which is that basically for low-income applicants, it made it almost impossible to relocate, to be allocated if you're outside the community. But for middle-income units, it had almost no effect. And so, so there's all of these examples of affirmative action sort of not having predictable or intended consequences. And there's a bunch of papers kind of talking about each of these and analyzing them. And so as motivation for the work that Jay and Carlos and I are doing, I would say I was both inspired and concerned looking at this literature. So I'm not going to go through the papers in detail, but sort of what I found inspiring is that if you just read one of these papers, it's great. Like they talk about what's going on in a particular application. They give you sort of the relevant constraints or considerations. There's usually some theory analyzing, here's different ways of doing things. And I think these papers could really be helpful towards improving allocation problems. So that's if you look at one paper. But if you look at the collection of papers as a whole, I would say it starts to get a little bit more concerning for two reasons. So one, the papers are often saying very similar things, but using slightly different language, slightly different definitions that are sort of tailored to their application. And so it can be hard to know, wait, has this result already been proven somewhere else, or how does it relate to this other finding for this other context? So that's sort of, as an academic, a little bit unsatisfying. At a practical level, I would say the more concerning thing is that there are so many papers like this being written right now, right? It's just, it almost seems like every time someone tries to implement an affirmative action policy, it has a bunch of unintended consequences that they don't really understand. And yeah, it's great as academics to try to write about these settings and sort of quote unquote fix them, but we're never going to be able to keep up, right? I mean, there's just so many different contexts in which these policies are being used that if we require an academic consultant to work on every one of them, we can't scale that. And in particular, for those of you who maybe live in the United States like I do, one thing I'm a little bit worried about is that I don't want to play the role of TurboTax, right? Where TurboTax basically lobbies to help keep our tax code super complicated so that people like me who don't want to dive into all of the details will pay them to sort of explain how we should do our taxes to us, right? And so similarly, I don't want market designers to be going out there implementing sort of complex systems that only they understand. And so the sort of motivation for this work is, like, instead of helping people use complicated systems, ideally, we would help them design simple systems that sort of achieve their main goals, but that they can understand and modify on their own without help from academic consultants. Okay, so that's the goal. The challenge, of course, is saying, what do I mean by a simple system? And I don't think there's a universal answer to this, right? So that's what I'm hoping to do. And so sort of in addition to identifying what I'm going to call explainable policies, I'm also hoping to do some unification of the literature. Okay. So what's going to go on in the rest of the talk? First, I'm going to give an axiomatic characterization of explainability. Right? And so this is going to identify a class of policies that I'm going to call outcome-based selection rules. And I'll go into more detail about what these are in just the very next slide. But outcome-based selection rules, it turns out, are going to, not all rules that you might want to use are going to be outcome-based selection rules. So here's two selection rules you might use that seem very similar, right? One is, let's start by hiring the highest ranking woman, and then we're going to hire the highest ranking remaining candidate. The other is, let's start by hiring the top candidate overall, and then we're going to hire the top woman that's left. And both of these types of policies are used in practice, but actually only one of them is going to be an outcome-based selection rule. In other words, according to our theory of explainability, only one of these rules is going to be explainable. And it's the one on the left. So after I've introduced this class of outcome-based selection rules, I'm going to tell you a little bit about why I think they're cool, and I'm not going to use any math in that part of the talk. I'm just going to sort of informally argue about why I think they're cool. And then in the paper, we also have an examination of sort of special cases of these rules that we think are especially relevant to practice. I might talk about those very briefly in this talk, but probably I'd rather save more time for questions or other components. So I'll spend a little bit of time on this. But this last part is sort of our effort to unify the literature, because there have been lots and lots of other papers talking about reserves and quotas. Okay, so with that, let's go to the model. So we're going to go fully into our theory now. So in our model, we have a finite set of individuals, okay? And we know a bunch about these individuals. So you can imagine we might know their gender or their income or where they live or any number of other characteristics. So these are really distinct individuals that we know something about. And then we're going to have a priority order over these individuals. So in the affordable housing allocation example, you can think of this priority order as being generated by the lottery, right? So the city uses a lottery to put these people in a random order. And a selection rule takes that priority order as input and then says who's actually going to be chosen, who's actually going to get an apartment in that context. And so you may say, oh, it's kind of strange that you're specifying a selection rule in this particular way, which is it takes as input a priority order and produces as output a group of applicants. But I think for context, certainly for context where the priority order is random, I think this makes a lot of sense because you basically need to have a procedure in place up front that says, well, if the priority order had been different, who would we have chosen? And even in contexts like school choice, where maybe it's not, say, filling university spots, where it's often based on a merit score, not a lottery, you sort of need to set the policy in advance before you know what each individual score is going to be. You say, okay, how many seats do we want to reserve for this group, for example? So this is a selection rule. It just takes as input a priority order, produces as output who gets chosen. And so the kind of simplest selection rule that I can think of would be something like, we're going to just choose the top K applicants according to the priority order.
Nick,
and now that would be, yep, there's a question.
Yes, just a clarifying question. Individuals, do they have preferences over the objects or not? You are not considering preferences.
Right, so in our model, we're considering there's like one homogeneous item with many copies. So individuals prefer to be allocated versus not, but in some sense, we're not going to ask individuals to report anything. They're not going to actually play an active role in this process. So you can sort of think of this in the affordable housing example, maybe there are many buildings and you have some decision about which buildings you want to apply to, but I'm sort of zooming in on once you've made that choice, now the building has to decide who to choose. And let's study and understand how the building makes that choice.
Thank you.
Yeah. So one way it could is just to take the top K applicants. But as we saw in practice, there are lots of other things we could do. We could start by looking at one group of applicants, then go to another, then go to a third, and so on. And so both of these would be valid selection rules. Okay, so now I want to define what it means for a selection rule to be explainable. Well, intuitively, I have in mind two different things that are related, right? So one is that if you make some change to the priority list, it should have sort of predictable consequences. Right? It would be weird if I could move Marion up one spot in the priority ranking, and then I'm suddenly choosing a completely different set of applicants. Sort of, it seems unrelated. So there should be some structure to how the set of selected applicants relates to the priority order. And then ideally, if we have this structure, what this will allow us to do is to explain to someone, say a disappointed applicant who wasn't chosen, explain to them why they weren't chosen. Okay, so that's the intuitive goal. Here's how I formalize this. And I formalize it with three axioms, and I would love your feedback, sort of maybe at the end of the talk about these axioms, because I think that's sort of the heart of the characterization that we have. Right. So the first axiom I think is pretty uncontroversial, which is just if you move someone up in the priority list, it should never hurt them. Right? In other words, if you were going to choose them with one particular priority order, And then you take a different priority order where the only difference is that you've taken that person and moved them higher, kept keeping everyone else the same, then you should still choose them. So that's the first axiom. Second axiom is what I'm going to call lower invariance. And so this says that if I look at some individual I, and I look at a particular priority order for the applicants, and now I'm trying to decide, should I get selected or not? This is only going to depend on the ranking of people above I. If I sort of shuffle the rankings below I, that's not going to change I's outcome. And so the idea here is if I tried to explain to I, for example, why weren't you chosen? And I did, my explanation started with, well, you're ranked number 6, but if you look at numbers 10 and 11, because 10 was above 11, I couldn't choose you. But if 11 had been above 10, I would have chosen you. Number 6 might say, why are you talking to me about 10 and 11? I have higher priority than both of them. And so, so I'm saying it shouldn't really matter whether 10 is above 11 or 11 is above 10 when deciding what happens to number 6. Now, I could still choose number 10 or 11. For example, I could say, candidate number 10 was from the community and you are not, and that's why 10 was chosen over you. But notice that that doesn't reference, the relative ranking of people below me. The third axiom I'm going to call non-bossy. And this is maybe a little bit of a slight misnomer in the sense that traditionally in the literature, non-bossy means that, or a mechanism is bossy if I can change my report in a way that doesn't affect me, but affects other people. Right? That would be the traditional definition of a bossy mechanism. Then a non-bossy mechanism would just would mean that's not possible. Here, agents aren't making reports in our model. And so but this it has a very analogous meaning, which is if you change an individual's priority ranking in a way that doesn't affect their own outcome, then it should also not affect anyone else's outcome. So if I move Marian up on my list, but I was going to choose her before, I move her up, I'm still going to choose her. The fact that I moved her up should not affect anyone else. So these are my 3 axioms. Any questions on the definitions of these axioms? Okay, so sometimes absence of questions means everyone's happy and they're following and they like the axioms. Sometimes it means that you don't understand the axioms or you think they're lousy. So I'm not sure exactly what to interpret. But these are my axioms for explainability, as it were. So a natural question from here is, can we actually get all 3 of these at once? And the answer is yes, and it's pretty easy to see that the answer is yes. For example, the first rule on the previous slide that just choose the top K applicants, it's pretty easy to see that that will satisfy all 3 of these, right? If I'm choosing the top K, if I move you up, it can never hurt you. Whether you get selected or not doesn't depend at all on how people below you are ranked. And if I move you up in a way that doesn't change your own outcome, it also doesn't change anyone else's outcome. So clearly we can get all 3 of these axioms. The question is sort of how big is the class? That the choose the top K is not a very rich class. So if we want to implement affirmative action policies, we couldn't do that with that simple policy. But actually, it turns out these axioms are satisfied by a much bigger class of rules, which I'm going to call outcome-based selection rules. And so the idea is, if we think about the New York City developer screening algorithm, it was sort of described algorithmically, right? Like start with this group, start at the top, try to process this group first, then try to process this other group, then try to process this third group, and so on. Instead of doing that, we could really just say, what are the feasible outcomes, right? So suppose you picked this set of individuals. Is that allowed or not? And now if I specify for you which are the feasible outcomes, now we still need to have some algorithm for choosing among feasible outcomes. But the algorithm we're going to propose is very, very simple. It basically is start at the top of the list and ask for the first person, is there a feasible outcome that contains this person? If yes, I'm going to take them. Now go to the next person on the list and ask, is there a feasible outcome that includes this person as well as everyone that I've already committed to that's higher on the list? If yes, I'm going to take the next person. If not, I'm going to skip over them. So it's basically like a serial dictatorship starting from the top in essence. So let's just do this with an example to make sure that's clear. Suppose we have 5 applicants and we're only going to choose 3 of them, but we can't just choose any 3. In particular, here are the 6 subsets that we could plausibly choose. Now, if the priority order is 1, 2, 3, 4, 5, we'd start and we'd say, can we accept applicant 1? Yes, we can. Okay, so we're going to take 1, and now we're not going to choose either of the subsets that don't include 1. Now we look at applicant 2 and we say, can we take 2 given that we've already committed to taking 1? And the answer is yes, we can. Okay, so we're going to accept 2. Now we say, can we take 3 given that we've already committed to taking 1 and 2? And now the answer is no. So we're going to skip over 3, take 4, and then that determines that actually our selection must be 1, 2, 4. Alternatively, maybe the priority order was going to be different. So if the priority order was 5, 3, 4, 1, 2, we'd start by taking applicant 5. That rules out 3 of these selections right off the bat. Unfortunately, that means we have to skip over applicant 3 because there's no feasible selection where 3 and 5 are chosen together. But we can take 4 and we can take 1. And so then this is the final selection that we would get in this case. So that's how an outcome-based selection rule works. It's really just defined by a set of feasible outcomes. And these feasible outcomes are exactly how we can encode affirmative action policies, right? So for example, I could say an outcome's not feasible unless you've chosen at least 3 women, right? Or unless you've chosen at least 3 women and at least 4 low-income applicants. And so, as you probably have guessed, right, it turns out that no matter how we define these feasible subsets, for any feasible subsets, if we take this rule and we apply it, we get a rule that is monotonic, lower invariant, and non-bossy. And we also have a converse, which is that if you want a rule that satisfies these 3 properties, then no matter how you describe your rule, it must be equivalent to having an underlying set of feasible subsets and then just applying this rule for that set. Right? So basically, if you want these 3 properties, you have to use an outcome-based selection rule. Okay, so why do I think outcome-based selection rules are really cool? Well, I would say two things about this idea. Right? One is actually it's telling us, on the one hand, there's a rich class of outcome-based selection rules. On the other hand, it doesn't include everything that's being used in practice. Right? And so it may be sort of helping to explain why certain policies people just don't understand. And so it rules out some existing policies. And then the second thing it offers us is a new way to describe policies that we may already be using. So let me give you an example of both types of advantages. So it's going to go back to these 2 selection rules we had before, right? One is start by hiring the top ranked woman and then hire the top remaining candidate, regardless of their gender. The other is start by hiring the top candidate and then hire the top remaining woman. Okay. And now these types of rules have already been well studied. And there's a number of papers documenting that people sort of don't understand the difference between these rules, right? Like they seem very similar. If you ask them, how will the outcomes of these two rules differ? People sort of struggle to reason through it. Now, what I claimed is that selection rule 2 actually doesn't have an outcome-based description. And how do I know that? Well, one way I know that is by using the characterization on the previous slide, which is this rule is actually bossy. So here's an example walking through it. I think the key thing about this is that we have 1 man and 2 women that have applied. If the order is 1, 2, 3, we're going to choose the top candidate, number 1, who's a man, and then we're going to choose the next ranking candidate, number 2, who's a woman. Okay. If the order is 2, 1, 3, we're going to start by choosing the top candidate, who's a woman, and then we choose the top remaining woman, number 3. So we end up choosing 2 and 3. Now, I'm not necessarily saying this is wrong or a bad rule, but first of all, this illustrates that it's bossy because we moved 2 up. We didn't change either way. Applicant 2 is selected, but where applicant 2 ranks in the priority list affects whether we choose 1 or 3. So that's why it's bossy. A different way of thinking about this is, hey, wait a minute. If we were willing to accept that we would take applicants 1 and 2 when they were ranked 1st and 2nd, then if we just switch their order and rank them 2nd and 1st, shouldn't we still be willing to take applicants 1 and 2? And so that's sort of why this doesn't have an outcome-based description. Right? You couldn't describe it in terms of a set of feasible selections. Whereas selection rule 1 does. In particular, selection rule 1 is equivalent to just saying the following: look, we're going to choose 2 people, and at least one of these people has to be a woman. Subject to that, we're going to try to take the kind of highest priority people that we can. And so what I want to point out here is if we look at selection rule 1, here we now have 2 different descriptions of the exact same rule. Right? So who gets chosen between the top and the bottom is the same. It's just a different way of describing the procedure we're using to choose. And I think the outcome-based description is a lot clearer because, and not only a lot clearer, I would say, makes it a lot easier for people to weigh in. So one thing that often happens in affirmative action type policies is that there's political processes that are sort of determining what the policy is, right? Politicians have to set them, people elect these politicians, they protest, and a lot of times they're very high stakes and high profile debates. Yes, I see that there's a question.
Yeah. Oh, so Nick, is the following true? Give me a set of feasible outcomes. If you pick me one outcome among this set, I can construct a priority order so that that's going to be the outcome that's selected by this algorithm. I don't know if this question makes sense or not.
So you're saying if you have a feasible selection,
yeah,
will there always be some priority order that picks it?
So here's the way that I read, and maybe I'm misunderstanding this. So there is a set of feasible outcomes, right? And among those feasible outcomes, I want to pick one outcome.
Yeah.
Right.
So the feasible outcomes basically encode the affirmative action. Mm-hmm. And then the one outcome I choose is going to be determined by the priority order.
Correct. So the question is, if you give me one outcome among those feasible outcomes, are you going to be able to find me a priority order so that the procedure that you described is going to select that outcome?
Not always. Mm-hmm. And here's why not, right? So for example, I could say, the feasibility constraints are, I could take at most 5 people, right? So now a selection with only 4 people is feasible according to that definition. But when I follow this algorithm, no matter what the priority order is, I'm going to always choose 5 people. Right. So I think what is true is that the maximal elements in the set inclusion sense of the feasible set, those you can always find a priority order that's going to pick them.
Thank you.
Thanks for the question. So why do I like outcome-based descriptions? I think that if we acknowledge that there's going to be a political process and a back and forth, we want people weighing in on things that they care about. So let me give you an example, a metaphor, let's say. Okay. So suppose someone asked me, here's a picture. This is a picture from a chair manufacturing plant, right? So we have a bunch of machines. Notice that along the left, there's all these dials and knobs that can be turned to adjust settings on the machines. Suppose someone came to me and said, hey, we're trying to improve our chair making process. Do you think we should turn knob number 6? And should we, we could move it a little bit to the right. Should we do that? I would have absolutely no clue how that actually affects the final chair that we're producing, right? But if they came to me and they said, look, we're producing chairs, what features are important to you in a chair? Then I could say, okay, well, I think the seat should be, 18 to 20 inches off the floor. I think it's important to me that the chair can support people of different weights, so maybe up to 300 pounds. And I really don't like sitting on chairs that don't have a backrest, so I think every chair should have a backrest, right? I can sort of weigh in on what the final outcome of the process should look like, even if I don't know how to tweak the process to make that outcome happen. And I would say similarly, I think in these sorts of selection problems, people often have in their minds, this is what we're going for, right? We want to make sure that these groups are represented at least this much, but not too much, or that there's sort of balance between these different groups, right? So they have opinions on the final outcome. But if you ask them, hey, should we be processing community residents before city employees or city employees before community residents in the algorithm, you're basically just asking them to turn a knob, and they're going to have no idea kind of what are the consequences of doing this. So I think it makes sense to focus attention on the feasibility constraints rather than on the algorithm. The second advantage, I think, is that after the fact, ex post, so the first one was kind of ex ante, when we're deciding what policies should be, we can ask people to weigh in. The second advantage is ex post, we want to tell people who are disappointed, why weren't you chosen? Right? And if we look at this first description, let's just focus on selection rule 1. If we look at this first description and we have someone who's not chosen, in some sense, we can explain to them why they weren't chosen. I mean, we can actually just publish the algorithm. This is what we did. You can verify that at each step of the algorithm, you're not chosen. You were not the top woman. And then after we hired the top woman, you were not the top remaining candidate. And so we didn't choose you. But I find it much more compelling, especially in more complex environments, to be able to say the following. Look, notice you weren't chosen. I'm sorry about that. But if I wanted to choose you, here's what would have had to happen. First of all, I have a set of constraints I'm dealing with, right? I have to choose a selection that satisfies certain rules. And so if I wanted to choose you, either I would have had to violate those constraints, or I would have had to displace someone who I'm currently choosing that has higher priority than you. And so I couldn't do either of those things. And so that's why you're not chosen. Right? There's actually no way to choose you without either violating constraints or choosing someone who has a higher priority. And notice that that was not the case for the New York affordable housing example. Like, we actually could have chosen person number 6 without violating constraints and without displacing anyone with higher priority. And so that right away tells you that they're not using an outcome-based selection rule. Okay, let's see. How are we doing on time? Okay, have a few minutes left, so I'm going to probably as I thought, not spend very much time on this. The point is just that all of the theory I've presented so far has been for a completely arbitrary set of feasible selections. In practice, we're not going to use arbitrary sets. There's sort of certain structure that we expect a lot of the feasible selections to have, right? If you have a completely arbitrary set, the rules that I'm advocating for may actually make really stupid decisions. So, for example, suppose that Arnosti is number one on the list, but for whatever reason, my feasibility constraints are if I take him, I can't take anyone else. Well, then when I start at the top of the list, I'm going to choose him and nobody else. But maybe there was a different feasible selection that could have included like everyone else in the seminar except him, and maybe I prefer that. But what we sort of show is that for natural feasible sets that have certain structure that we see in practice, in many cases, you don't have these sorts of degeneracies. So you can basically use this greedy procedure, and you end up choosing the optimal subset. And so I'm not going to go into the details of this. For those of you that know greedy optimization, we're using matroid theory. We're showing that certain feasible sets induce a matroid. Not always, right? So for example, what we show with quotas is that only under fairly restrictive structure on the quotas do you actually get a matroid. And so in some cases, you will end up with situations where maybe if you follow this policy, you won't be maximizing the total number of people who get chosen. So I think I'm going to skip through these examples. I mean, I'd be happy to talk to you more about what we do for reserves, but I think this is more about showing that many existing results can be sort of captured with our framework and existing rules. We do have some new mathematical results, but in the interest of time, I'm going to skip past and close here and let you ask any questions or provide any comments that you may have. The basic idea of the work, though, just to summarize, is that affirmative action policies, I think, are playing an ever-increasing and important role. And there are a bunch of papers that are really cool looking at different affirmative action policies that are in place. But in some sense, I think these papers are sort of helping us understand the intricacies of ever more and more complex policies. And maybe we should take a slightly different tack and say, hey, can we use simple policies in some formal sense, policies that are simple but are flexible enough to accommodate the things we care about? And so our proposal is that maybe outcome-based selection rules are the way to do that. Thanks a lot.
Could I ask a question?
Yes, please.
Yeah, thank you for the talk. That was very informative. So I was thinking, so one of the active research areas in machine learning is explaining how clustering works. So you can think of clustering as giving you like a final selection of different groups of items in a set. So you could emphasize, you could enforce like the final outcome as you've done here. But the question always has been, how does the algorithm actually select the items in each cluster? So if I wanted to make your algorithm more transparent, so we know what the final outcome is and we can enforce it, but how does the algorithm actually go through each step? I was thinking maybe, have you thought about applying some sort of a decision tree so that you can kind of lay out step by step how each person was eliminated or selected to get to the final outcome?
Yeah, so in principle, one thing you could do is, you could imagine literally enumerating all of the feasible sets. And then you could say, okay, I took applicant 1. At that point, I've eliminated these 2 sets. I took applicant 2. Now I've eliminated these 2 sets. Oh, at this moment, this is the first moment at which applicant 3 could no longer be selected. right? And so I could sort of explain to applicant 3, look, once I'd committed to taking 1 and 2, there was no way you could be chosen. You'd been ruled out at this moment of the algorithm. So that would maybe be one way to try to offer that explanation. And I think that's one advantage of the sort of greedy processing that we're doing here, top down, is that I can explain to applicant 3 why they couldn't be selected, and my explanation is only going to involve people that are higher ranked than applicant 3. Now, of course, for general feasibility sets, we often have additional structure. And so, enumerating every possible feasible subset may not be sort of computationally advantageous and so on. But I would say conceptually, this is the way that I find clearest to explain to someone why they weren't chosen.
Great, thank you.
Other questions? Or not questions? Comments? Concerns?
Well, maybe not really a question. I was just wondering, your title is Explainable Affirmative Action, and then you motivate the axioms by explainability, and you end up that those are outcome-based, the selection rules. And in the end, you gave us these 2 advantages. One is the outcome-based thing, and the other is the explainability. So I was just wondering whether it's necessary to start from explainability, and if yes, why you chose.
Yeah, this is a great question. I mean, you summarized succinctly. So there's sort of, I would say, 2 ways one could motivate outcome-based selection rules. And I sort of intuitively, I just think this is a good way to approach these types of problems, right? Because of the sort of public policy side of things, that I think when you see people debating these policies, what you see them talking about are, they talk about how should we produce the priority ranking. So for example, in New York City, should students be ranked based on exam scores, or is that unfair and they should be ranked based on other criteria? And you see people talking about feasible outcomes, like should we put some minimum quota on a particular group? You don't see anyone in public talking about the choice between different algorithms for using these inputs. And so sort of intuitively, I just think I want the algorithm to be fully specified by the 2 things that people actually seem to be able to form opinions about. And that's I would say, a philosophical belief I have. However, there's no math there. It sort of feels a little bit fuzzy and kind of hard to argue, well, is this really a good idea or not? Someone else might disagree. And so the axioms are my way of trying to sort of formalize, well, if you think we want these 3 axioms, then you really have to do something, use an outcome-based selection rule, do something like this. And if you don't like my conclusion that we should use outcome-based selection rules, and you think we should be using something else, then you should be able to point to at least one of my axioms that you don't think is very important. And so maybe we can have a more focused conversation about, like, okay, this axiom, I don't really like it. I want to use a rule that violates it because I think it has some other advantage. So I agree with your premise, basically, that I have sort of competing motivations. Like, explainability is one aspect of it, but there's sort of multiple reasons why I think that these selection rules might make sense.
I just thought in the political process, the first motivation with the outcome-based arguments would come first, and the explainability, we would have to think from the end, that at the end you have to explain the outcome to somebody. But the argument with the first advantage you brought would, in a political process, maybe be easier to make.
Yeah, totally. So I think the advantages have more or less salience in different applications. I do think in a lot of these public-facing processes, it's sort of important to be able to explain to someone why they weren't chosen. And for them to feel like there was due process. And then if they don't like the rules that made it so they weren't chosen, they can try lobby to change those rules, but at least they kind of know the rules were followed. And so I think that often has value, but I agree that, not always. It sort of depends on context. And also there's a question of like, what counts as explainable? So for example, I said, the advantage of this is I can tell you choosing you would require me to either violate the constraints or displace someone of higher priority. In one sense, that's a very succinct explanation of why you weren't chosen. In another sense, maybe actually it's difficult to verify that my statement is correct, right? Like, how do you know that there isn't another feasible selection involving you and the people higher than you? And that can be actually a computationally difficult thing. And so, I think computational concerns are usually not of first order in these problems. So I'm not so concerned about that. And I like these explanations, but I think someone else could say, well, is that really a good explanation if you can't sort of prove to them that your statement is correct?